Welcome to Electrochemistry. I know what you're thinking. You are already familiar with the basics of electrochemistry. In truth, we studied the effects of electric current on substances in level 2 of video books. We noted that ionic compounds conduct current either in aqueous or molten states. We saw that when an electric current flows through a molten or an aqueous ionic compound, the compound is decomposed in the process. This we called electrolysis, and such compounds we call them electrolytes. In particular, when electric current was passed through molten lead-2 bromide, a red-brown bromine gas is liberated at the anode, while grayish beads of lead are deposited on the cathode. We said that in molten state, lead-2 bromide dissociates into lead and bromide ions. At the anode, bromide ions are oxidized to bromine gas, and at the cathode, lead ions are reduced to lead metal. Overall, we said that both oxidation and reduction reactions occur, and we called this a redox reaction. In this chapter, it will be interesting to note that not only does electrical energy produce chemical reactions, but chemical reactions themselves can also generate electrical energy. We shall look at how chemical reactions produce electrical energy, and in turn how the electrical energy causes chemical reactions. So let's get started, and exactly what is a redox reaction, and let's briefly demonstrate a redox reaction. Now on the screen I have a blue solution of copper 2 sulfate. By now you should have noticed that copper ions are always blue in color, and that gives the copper salts blue color. And again I have ion fillings. If I add the ion fillings to the blue solution of copper 2 sulfate, see what happens. There is a red-brown solid deposited, and the solution turns light green. The brown solid is copper metal, and the solution turned light green due to formation of ion to ions. The reaction that has just taken place involves transfer of electrons from one species to the other. The ion lost 2 electrons to become an ion to ion according to this ionic equation, and therefore it goes into the solution. The copper ions in the blue solution gained the 2 electrons that were lost by ion to become copper atoms, again according to this ionic equation. The copper is deposited as brown solid. Ion to ions are always light green, and hence the color of the solution. Generally, with reference to electrons, oxidation is the loss of electrons and reduction is the gain in electrons. Iron is oxidized to ions, while copper is reduced to copper atoms. The 2 separate equations are called ionic half equations. If I combine the 2 equations, I will come up with this, and this is a complete ionic equation for that redox reaction. Now note the way the half equations are written, especially the loss of electrons and also the change in state symbols from aqueous to solid and vice versa. For a redox reaction to occur, one substance must be oxidized and the other must be reduced. The electrons lost by one are the same electrons that are gained by the other. The substance that loses electrons is said to be oxidized. Itself is called a reducing agent. Why? Because it causes the reduction of the other species. The one that gains electrons is said to be reduced and is itself called an oxidizing agent. Why? Because it causes the oxidation of the other. Oxidation numbers. Now you and I know that oxidation number is simply the charge that an element, compound, or an ion carries. This is important. Why? Because it helps us know and keep track of the electrons' movement in redox reactions. When redox reactions occur, electrons are transferred, charges change, and the oxidation states of involved substances change as well. But just how do we tell the oxidation states and numbers of substances? There are simple rules that will guide you to do this. The first rule involves ions containing one element, and the oxidation number of such ions is simply the charge on that ion. For example, an aluminium ion has an oxidation number of positive 3. Calcium ion has an oxidation number of positive 2. Chloride ion has an oxidation number of negative 1. Oxygen ion has an oxidation number of negative 2. Sodium ion has an oxidation number of positive 1, and many others. Rule number 2 involves uncombined elements and molecules, and the oxidation number of such substances is 0. For example, magnesium, aluminium, sodium, potassium, chlorine gas, hydrogen, bromine, and oxygen all have oxidation numbers of 0. The third rule involves hydrogen. Now, hydrogen has an oxidation number of positive 1 in all compounds except metal halides, where it is negative 1. For example, in hydrochloric acid, the hydrogen has a charge of positive 1 and the chloride has a negative 1. In sulfuric acid, the hydrogen again has an oxidation number of positive 1. We have sulfur has an oxidation number of positive 6, and oxygen has negative 2. However, if you come to sodium hydride, you will find that hydrogen has an oxidation number of negative 1, while sodium has positive 1. In magnesium hydride, the story is the same as in sodium hydride. Now, you should notice that hydrogen can form a cation or an anion by either losing the only electron or gaining another electron to complete a doublet configuration. Rule number 4 involves oxygen. And oxygen has an oxidation number of negative 2 in all compounds except in peroxides, where it is negative 1, and in oxygen difluoride, where it is positive 2. For example, in sodium hydroxide, the oxidation number of oxygen in that compound is negative 2. Zinc oxide, the same, it's negative 2. In sodium peroxide, it is negative 1, and sodium in that sodium peroxide is positive 1. In oxygen difluoride, you realize oxygen has an oxidation number of positive 2, while the fluoride has an oxidation number of negative 1. Next, we have radicals, and overall charge is the sum of the oxidation numbers of the constituent elements. So if you look at carbonate has an overall charge of negative 2. How do we arrive at that? We simply add up. Carbon has an oxidation number of positive 4, plus oxygen has an oxidation number of negative 2, and there are 3 of them. So we have 4 plus negative 6, and we end up with negative 2. That is the oxidation number of the radical carbonate. Ammonium ion, it has an oxidation number of positive 1. The overall charge is positive 1. How did we get there? Nitrogen has an oxidation number of negative 3. We add 4 hydrogen with oxidation numbers of 1 each. If we do that, we'll get the positive 1. Hydroxide, the oxygen has an oxidation number of negative 2, and we add positive 1 for hydrogen, and we get negative 1. The last rule, rule number 6, involves compounds. and the sum of the oxidation numbers of constituent elements in a compound is equal to 0. Really, the overall charge on a compound is 0. For example, sodium chloride, sodium is positive 1 and chlorine is negative 1. If you add plus 1 plus minus 1 is equal to 0. Carbon 4 oxide, carbon has an oxidation number of positive 4 and oxygen has negative 2, and there are two of them. So plus 4 plus minus 4 would give us 0. Now, this is very important in calculating the oxidation numbers of elements in compounds if we did not know them. For example, what is the oxidation number of manganese in potassium permanganate? What is the oxidation number of manganese in potassium permanganate? First of all, notice that the name potassium permanganate is not a very appropriate name. Why? Because it is not the IUPAC recognized name. But I'm not using the IUPAC name. Why? Because if I should do that, then I'll be giving you the answer directly. Now, the chemical formula for potassium permanganate is as on your screen. Now, the oxidation state for potassium is positive 1. The oxidation number for manganese, which we are looking for, we will assign it M, and that of oxygen we know it's negative 2. So we have plus 1 plus M plus 4 times minus 2. There are two oxygen that should sum up to 0. So 1 plus M minus 8 is equal to 0. M is positive 7. And therefore the oxidation number for manganese is positive 7. Actually, the IUPAC name for that compound is potassium manganate 7. Potassium manganate 7 is the IUPAC name, and that gives you the oxidation number for the manganese. Again, let's look at the oxidation number for the chromium in dichromate ion. Now you realize the overall charge on our species is negative 2. So the sum of the oxidation numbers should give us negative 2. Now we assign the oxidation number of chromium as C. So there are two of them. I'm going to have 2 times C plus 7 times minus 2 should give me minus 2. So 2C minus 14 is minus 2. 2C is 12 and C is positive 6. So chromium is positive 6. That is the oxidation number. Now, in your own time, find the oxidation number of sulfur in sulfuric acid and nitrogen in nitric acid. Now, is all this really important in chemistry? Well, yes, very important. Why? Because the change in oxidation numbers during a reaction can be used to show that a redox reaction has occurred. How about that? Look at this. In the preparation of chlorine gas, we react potassium manganate 7 with hydrochloric acid. In truth, this is a redox reaction, but by just looking at it like that, you cannot be able to tell, can you? No. But if we look at the oxidation numbers of individual elements in the reactants and then find the oxidation numbers of the same elements in the products, you will find that the oxidation numbers of some of them actually change, meaning that oxidation and reduction occurred. If you look at the reactants, potassium in potassium manganate 7 has an oxidation number of positive 1. Manganese, we've just seen, has positive 7 and oxygen has negative 2. In hydrochloric acid, hydrogen has positive 1 and chlorine has negative 1. If we look at the products, the oxidation numbers are as on your screen. Potassium +1, chlorine has -1. Manganese in manganese 2 chloride has +2. Chlorine has -1. In chlorine gas, the oxidation number is 0. The oxidation number of molecules is 0. In water, hydrogen has +1 and oxygen has -2. Now, if you look at the oxidation numbers of the elements in the reactants and then look at the oxidation numbers in the products, you notice that some of them changed, some of them did not. So let's look at that. Potassium has remained +1 both in the products as it was in the reactants. Manganese changed from +7 to +2 in manganese 2 chloride. Oxygen remained the same, -2. Hydrogen again no change, it remained +1. Chlorine changed from -1 in hydrochloric acid to 0 in chlorine gas. Now, if you look at that, you realize manganese 7 is reduced to manganese 2, and chloride ions were oxidized to chlorine gas. Now, you can see there is full evidence of a redox reaction. There was reduction of manganese 7 to manganese 2 and oxidation of chloride ions to chlorine gas. Now that is a redox reaction. Now you need to try as many examples as you can. Most of the reactions are actually redox. But if you look at them just like that, it is usually impossible to tell. Now some elements form ions with varying oxidation numbers. For example, we have ion 2 with an oxidation number of +2 and ion 3 with an oxidation number of +3. Again, we have copper 1 with an oxidation number of +1 and copper 2 with an oxidation number of +2. Now the numbers in the bracket indicate the oxidation state. Now these numbers are usually written in Roman, but it is only a way of telling us the oxidation numbers. For instance, in nitric 5 acid, also called nitric acid, nitrogen has an oxidation number of +5. In nitrous acid, also called nitric 3 acid, the nitrogen has an oxidation of +3. Now, still in redox reactions, let's look at what we call displacement reactions. Now, when we added iron to a solution of copper 2 sulfate, the following reaction took place. That iron, the solid, reacted with copper 2 sulfate to form iron 2 sulfate, which was light green, and copper solid, which was deposited at the bottom. From this equation, you can see that iron displaced copper from the solution of copper 2 sulfate. You know why? Because iron is more reactive than copper. So iron reduced copper ions to copper atoms. Generally, a more reactive element will displace a less reactive element from its solution. More reactive elements are also stronger reducing agents. Now, if you look at this chart, potassium is at the top there. It is the strongest reducing agent, and it is also the reactive of all those. It is the most reactive of all those other elements, followed by sodium, calcium in that order until we have silver, which is the weakest reducing agent and the least reactive on that list. Now, this tells you that magnesium will reduce zinc ions to zinc solid. According to this ionic equation, you realize magnesium, when added to a solution of zinc ions, magnesium will go into the solution and the zinc will be deposited as a solid metal. Again, copper will reduce silver. Copper solid, when reacted in a solution of silver ions, it will form copper. Copper will go into the solution to form copper ions and silver metal will be deposited. So copper will reduce silver ions to silver metal, and the copper itself will be oxidized to copper ions, which will go into the solution. Now, these redox reactions are often seen by color changes, the change in solution color. For example, when we had the reaction of iron and copper to sulfate, you realize the solution turned from blue to light green. Now, this doesn't only work for nonmetals or ions. More reactive nonmetals will displace less reactive nonmetals from their solutions. For example, chlorine will displace bromine, which will displace iodine, and that order follows like that. Now, so much for redox reactions. Let's now look at another area of electrochemistry. That is an electrochemical cell. Now, an electrochemical cell may either be a galvanic or electrolytic. In a galvanic cell, also called voltaic cell, chemical reactions trigger the flow of electrons to generate electrical energy. On the other hand, in an electrolytic cell, the system is connected to a source of current like a battery, which will trigger the electrons to flow. In other words, in electrolytic cells, the electrical energy triggers the flow of electrons and subsequently cause the chemical reactions to occur. Now, before we indulge deeper into the galvanic and electrolytic cells, let's look at something we call electrode potential. Now, when a metal rod is dipped into a solution of its own ions, some atoms of the metal will dissolve as positive ions, leaving behind electrons which will build up on the metal surface. How? For example, if I have a copper rod and dip it into a solution of copper 2 sulfate, some copper ions will dissolve into the solution and the electrons will be left on the copper surface. So you will see over time that the metal dissolves away and the blue color of the solution becomes deeper and deeper as the metal size becomes smaller and smaller. That is, it's losing mass. Now, this will continue until a sort of equilibrium is established and won't go on forever. Now, from this ionic equation, you can see that the copper solid is losing electrons and it's going into the solution as cations, that is, copper ions. Now, the metal surface is negatively charged while the solution is positive. A potential difference thus exists. If you remember, a potential difference always develops wherever there is separation of positive and negative charges. The concentration of electrons on the surface is given by a quantity called electrode potential. Now, this kind of an arrangement constitutes what we call a half cell. The tendency of metals to lose ions when in such a setup differ from one metal to another, and therefore the electrode potential also differs from one metal to another. Logically, it is not possible to measure the electrode potential of a single half cell. So what we do is that we connect two half cells and measure the potential difference between them. The difference causes flow of electrons. The potential difference causes the flow of electrons. For example, I can measure the potential difference between a zinc-zinc ions half cell and a copper-copper ions half cell using the setup as shown on the screen. The zinc rod is dipped into a solution containing zinc ions, for example zinc sulfate, and copper will be dipped into a solution of copper 2 sulfate. Now those are two half cells and the electrodes are connected via a cable. A galvanometer is used to measure the potential difference in volts. Now, if I leave the setup like this, nothing will happen. Why? Because the circuit is incomplete. No reading actually appears on the galvanometer. It's indicating 0. To complete it, we use what we call a salt bridge. The salt bridge is usually a tissue paper soaked in either potassium nitrate or sodium nitrate. The ions in the salt bridge must not react with any of those under investigation. To do that, you realize now that the electrons are flowing and the galvanometer has some readings. The next thing I know you are wondering is, why are the electrons moving from zinc to copper and not the other way around? Well, it's because of what I just called earlier, reduction potential. Let's first look at this reduction potential. Standard reduction potential. Now, you and I know that reduction potential differ from one substance to another. In order to measure or quantify the reduction potential of any metal, we need a standard that we shall compare with the other metals. The standard electrode that is chosen is that of hydrogen. This is called a standard hydrogen cell. Being the reference, it is assigned an electrode potential of 0.00 volts. The standard conditions for measuring the electrode potential are a temperature of 25 degrees Celsius, a concentration of 1 molar and a pressure of 1 atmosphere. A platinum is used as an electrode when the half cell does not include a metal. A hydrogen-hydrogen electrode consists of an inert platinum electrode immersed in 1 molar solution of hydrogen ions. Hydrogen gas is bubbled on the platinum electrode. Platinized platinum electrode allows hydrogen gas to be adsorbed on its surface. An equilibrium is established between the hydrogen gas and the hydrogen ions as indicated by this equation. The standard half cell is represented as shown here, and this is called a cell diagram, but this is a cell diagram for half cell. And the standard electrode potential denoted as E0 for this half cell, which is 0, can be represented as shown here. Now, the electrode potential for all other metals is taken as the difference between the metal electrode and the standard hydrogen electrode. For instance, electrode potential for zinc can be measured as shown here. The galvanometer indicates negative 0.76 volts. It is important to note that some metals like zinc have greater tendency to lose electrons than hydrogen electrode. Its electrode potential is therefore a negative. Others like copper have less tendency and their electrode potential is positive. The standard electrode potential for various metals are shown on this chart, and this data is actually documented and you need not to memorize any of the values. Standard electrode potential are sometimes called standard reduction potentials because they relate to the reduction of the oxidized species. From the table, the stronger reducing agent is the one with the largest negative. The strongest oxidizing agent is the one with the largest positive. So if you look at the table, zinc is a stronger reducing agent than copper. So back to our setup, we've seen that zinc has higher electrode potential than copper. What does that mean? That the zinc electrode has higher accumulation of electrons than the copper electrode. It is therefore relatively more negative with respect to the copper terminal. When the two half cells are connected, electrons flow from the zinc terminal through the wire to the copper terminal. Now these electrons are gained by the copper ions in the solution of copper 2 sulfate. Now, uses of electrode potential. Now, the electrode potential are important in one, comparing the oxidizing and reducing powers of substances. For example, from that chart we've just had, you could see that potassium is the best reducing agent, and it is followed by sodium. All the way we have zinc is better than copper, magnesium would be better than lead, and so forth up to silver. They're down like that, and you are able to know which of these substances will reduce the other. We can also use the electrode potential in determining the electromotive force of a cell. Finally, you can use the electrode potential in predicting whether or not a reaction will take place. We'll look at that at the end. So let's now look at how we use the electrode potential in determining the EMF of a cell, calculating the electromotive force of a cell. Now, it is important to note that in an electrochemical equation, the process that is indicated is a reduction one. On that chart, what was indicated is the reduction process. For example, in the reduction of zinc, we will have zinc plus 2 electrons to form zinc ion. And the E naught for that is negative 0.76 volts. That is the electrode potential for the reduction of zinc. Again, in a complete cell, one species is oxidized and the other is reduced. That's very, very important. For a redox reaction to take place, one species must be oxidized, the other must be reduced. If the above ionic half equation is reversed to show an oxidation process, the sign on the voltage is reversed as well. That is, zinc, when they are oxidized to zinc ions plus 2 electrons, the electrode potential now becomes plus 0.76 volts. That is very important for you to note. Remember also, the species that is oxidized is the reducing agent. That which is reduced is the oxidizing agent. Pretty easy to understand that. Thus, in comparing two species, the stronger oxidizing agent is the one that undergoes oxidation. And therefore, when comparing two species in a cell, the stronger reducing agent is the one that undergoes oxidation. And therefore, we reverse its ionic half equation and change the sign of the electrode potential. The EMF of the complete cell is the sum of the individual electrode potentials. For instance, let us have a copper zinc cell. From the chart, zinc is a stronger reducing agent than copper. Zinc will therefore undergo oxidation. Its equation will therefore reverse to zinc undergoing oxidation to form zinc 2 plus 2 electrons, and the electrode potential therefore reverses to plus 0.76 volts. Copper remains the same. Copper undergoes reduction. Copper 2 plus 2 electrons to form copper solid, and the electrode potential there is 0.34 positive. Now we add the two. To get the EMF, we add the two half equations, and we shall have zinc solid plus copper 2 plus to give us zinc 2 plus copper solid, and the electrode potential for that complete cell is the sum of the two, which is plus 1.10 volts. 1.10 volts positive. And if you look at our setup, the galvanometer is actually reading 1.1 volts. So next, let us pick magnesium and lead. Magnesium and lead, let's have that cell. So magnesium is a stronger reducing agent than lead, and therefore magnesium will be oxidized. We thus reverse the half equation for the reduction of magnesium to suggest an oxidation process. So magnesium undergoes oxidation to give us magnesium 2 plus 2 electrons. The electrode potential is plus reversed 2.37 volts. Lead undergoes reduction, so the equation is retained as it is on the chart, and the electrode potential there is negative 0.13 volts. So the electromotive force for that cell is the sum of the two electrode potentials. So we can have what we call an electrochemical equation where we have magnesium plus lead ions to give us magnesium ions plus lead solid with an electrode potential of plus 2.24 volts. Now these equations indicating the EMF is what I have called electrochemical equations. For each electrochemical cell we can have what we call a cell diagram as shown here. So for the first cell, zinc and copper, we have zinc undergoes oxidation to form zinc ions. We have the two strokes there indicating a salt bridge, and then on the other side copper undergoes reduction to form copper solid. The same case follows for magnesium and lead cell. Now I've said the double stroke indicates a salt bridge. Single stroke shows the potential difference between the electrode and its ions in the solutions. The species undergoing oxidation will always come first. So for a question, calculate the electromotive force for the electrochemical cell represented by the following. From this illustration, iron is oxidized to iron 2 ions while silver ions are reduced to silver solid. Even without checking, it is obvious that iron is a stronger reducing agent. So we reverse the equation and the sign as well. And from the chart, the electrode potential is negative 0.44 volts, so I'm going to reverse it to give me plus 0.44 volts. Silver undergoes reduction, silver plus electron to give me silver metal, and the electrode potential is plus 0.80 volts. Now you realize that we need to balance the electrons that are lost because they are the same number of electrons that are supposed to be gained. So we multiply the silver equation by 2. So we have 2 silver ions plus 2 electrons to give us 2 silver metal. But the electrode potential remains the same, and then we shall add the 2 and we shall get iron plus 2 silver ions to give us iron 2 ions plus silver metal with an electrode potential of 1.24 volts. 1.24 volts is the electromotive force for that iron silver cell. Now for your own assignment, write the electrochemical equations for these cells. That means you will have to calculate the electromotive force for these cells. What I've given you there are the cell diagrams. Now, from what we've just done, it is clear that an electrochemical cell that produces the largest EMF is that which constitutes a strong reducing agent and a strong oxidizing agent. When the electromotive force of an electrochemical cell is negative, the reaction is unlikely to occur, and this is used to predict whether a reaction will occur or not. Now, try this and see what you end up with. Copper and zinc cell. Now you realize copper cannot reduce zinc. Why? Because zinc is a stronger reducing agent than copper. If you calculate the EMF of this cell, you will see that it is a negative, and therefore it is not possible for copper to reduce zinc. Now that is pretty much about the galvanic cell and the electromotive force. Next, we look at electrolytic cell and electrolysis. An electrolytic cell is another type of electrochemical cell whereby the electrical energy is used to cause chemical decomposition. The chemical involved is called an electrolyte. An electrolyte is defined as a substance that conducts electric energy in aqueous or molten state and is itself decomposed in the process. This chemical decomposition of an electrolyte by electrical energy is what is called electrolysis. We saw the electrolysis of binary electrolytes, meaning that they had only two kinds of ions. For instance, the electrolysis of lead to bromide, there was only bromide ions and the lead ions. In this section, we look at the electrolysis where the electrolyte have more than two types of ions, usually ionic compounds in aqueous solutions. The other ions come from water since it also dissociates or ionizes as shown here. Water ionizes into hydrogen and hydroxyl ions. Now, in electrolysis, the electrodes are dipped into an electrolyte and then connected to a battery. The terminal is called the anode, and the one connected to the negative terminal is called the cathode. Negatively charged ions will migrate to the anode, and positively charged ions migrate to the cathode. That is basic law of electrostatics. Now, when more than one type of ions migrate to an electrode, only one type will lose or gain electrons, as the case may be, and this is called preferential discharge of ions. Conventionally, electrons are lost at the anode and gained at the cathode. Thus, oxidation occurs at the anode while reduction takes place at the cathode. Now, let us look at this practical electrolysis of water. So, we'll put water in this tray, and this tray has electrodes. We also have a battery, and then we shall have two test tubes filled with water, and they will be inverted over the electrodes. So now let us watch what happens. Now you notice bubbles of colorless gases being produced on both the test tubes. So finally, this is what we get. Now the gases produced are hydrogen at the cathode and oxygen at the anode. Again, notice that hydrogen gas is more than the oxygen gas. So let us see what happens. Water ionizes or dissociates into hydrogen and hydroxyl ions. That is according to this equation which we had seen previously. When the water is connected to a battery, the hydrogen ions migrate to the cathode. They are attracted to the oppositely charged electrode, while the hydroxyl ions will move to the positively charged electrode, that is the anode. Now, at the anode, what will happen? Hydroxyl ions will lose the electrons to form water and oxygen gas. That is according to this overall equation. 4 hydroxyl ions will form 2 water molecules plus oxygen molecule, and by that they will have lost 4 electrons. Now these electrons that have been lost by the hydroxyl group will travel through the conductor to the cathode. Now what will happen at the cathode? Now at the cathode, hydrogen ions acquire the electrons to form the hydrogen gas. Overall, we find 4 hydrogen ions gain 4 electrons to form 2 hydrogen molecules. Now, so overall, 4 electrons are transferred from the anode to make 1 mole of oxygen gas. 4 electrons are lost at the anode to make 1 mole of oxygen gas, if you look at that equation. And the same 4 electrons are gained at the cathode to produce 2 moles of hydrogen gas. And this is why the hydrogen gas is more than oxygen gas. So actually, at each and every point, the hydrogen gas is twice the volume of the oxygen gas. Now, the electrolysis of dilute acids and most aqueous solutions of ionic compounds will produce oxygen and hydrogen. For instance, the electrolysis of sodium chloride solution, there shall be 4 ions in the solution, that is hydrogen and hydroxyl from water, and then we shall have sodium and chloride ions from sodium chloride when it dissociates. Now, when that solution is connected to a battery, the hydroxyl and chloride ions will migrate to the anode, but it is the hydroxyl ions that will be discharged again to generate oxygen gas. The hydrogen and sodium migrate to the cathode. Sodium and hydrogen ions will migrate to the cathode, but hydrogen is preferentially discharged to generate hydrogen gas as was done earlier. So you realize the electrolysis of sodium chloride is simply the electrolysis of water based on the product that are produced, that is hydrogen and oxygen. Now, this preferential discharge of ions is by virtue of the electrode potential of those ions. Some ions are more easily discharged than others. For example, hydroxyl is more easily discharged compared to chloride ions. At the same time, hydrogen ions are more easily discharged compared to the sodium ions. So when the two ions migrate to the same electrode, one of them, which is more easily discharged, will be the one that will either gain or lose the electrons. However, in electrolysis of concentrated sodium chloride, otherwise known as brine, the situation is quite different. Now, at the cathode, hydrogen ions are discharged to generate hydrogen gas, and at the anode, the chloride ions are discharged to generate chlorine gas. Why have the chloride ions been discharged in preference to the hydroxyl ions, as was the case? Now, it is because of their high concentration compared to the hydroxyl ions. At the cathode, chloride ions are discharged because of their relatively high concentration compared to the hydroxyl ions. So you can see the chloride ions migrating to the anode. They lose the electrons and they become chlorine gas. Now again at the cathode, you can see the hydrogen ions migrating and they gain electrons to become hydrogen gas. Now notice that in this case the gases are in equal volumes. Why? Because for every 2 electrons lost by the chloride ions, 1 mole of chlorine gas is produced. Again, for every 2 electrons gained by the hydrogen ions, 1 mole of hydrogen gas is produced. Now the production of chlorine will not go on throughout. As the discharge continues, the concentration of chloride ions will decrease obviously relative to the hydroxyl ions, and eventually the hydroxyl ions will be discharged to produce oxygen gas as before. But it is the electrolysis of copper 2 sulfate that is so intriguing. Why? Well, first, because the copper ions are preferentially discharged to the hydrogen ions when they migrate to the cathode. And secondly, the observations differ depending on the electrodes used. Let's first see what happens when carbon electrodes are used. Now, once the circuit is complete, hydroxyl and sulfate ions will migrate to the anode. The hydroxyl ions are discharged to produce oxygen and water as shown on that equation. Now at the cathode, copper and hydrogen ions will migrate. Copper ions are discharged because they have a greater tendency to gain electrons compared to hydrogen. Copper metal is formed and is deposited on the surface of the cathode, and the equation for that reaction is shown there: copper undergoing reduction to form copper metal. Now you should also observe that the blue color of the solution fades away as the concentration of copper ions in that solution decreases. If you recall, we said it is the copper ions that give the solution a blue color. So when the copper ions are being reduced to copper, the intensity of that blue color fades away to become pale, and then it will be colorless. How about when we use copper electrodes? Now the setup is the same. At the anode, there are hydroxyl and sulfate ions, but none of them will be discharged. What will happen? Instead, the copper atoms in the electrode will lose the electrons and become copper ions and dissolve into the solution. Now this is a case of a metal being dissolved into a solution of its own ions. At the cathode, there are hydrogen and copper ions, and again the copper ions are preferentially discharged to form copper solid that is deposited on the surface of that electrode. So we observe that the anode is losing mass and the cathode is gaining mass. But you also notice that the color of the copper 2 sulfate doesn't change. Why? It is because as the copper ions are being discharged, more copper ions are released from the anode, and therefore there is a kind of equilibrium that will develop. Now the amount of copper oxidized at the anode equals to that deposited at the cathode. Now for any solution, we can predict which ions are preferentially discharged based on the ease of discharge as shown on this chart here. Now from all this discussion, it is clear that electrolysis is affected by 1. The position of the ions on the electrochemical series as shown on this chart. The ions that are more easily discharged are the ones that will be discharged preferentially when they are on the same electrode with other ions. Secondly is the concentration of the ions. And a cation or an anion that is high in concentration is preferentially discharged if the ions are closer in the electrochemical series. That is very important. The electrons must be closer in the electrochemical series. You will realize that chloride and hydroxyl ions are closer in the electrochemical series. So when chloride ions were in higher concentration, they were discharged preferentially to the hydroxyl ions. And now let's see the quantitative analysis of electrolysis. Now, during electrolysis, the amount of electricity passed determines the amount of the substance that is deposited. Electric current is measured in amperes, we all know that. The quantity of electric charge Q is measured in coulombs. A coulomb is the quantity of charge passed when a current of a given amperes is passed for a given time, usually in seconds. Therefore, Q is equal to IT, where I is current and T is time. For instance, if 3 amperes of current flow for 2 minutes, the quantity of charge is given by Q is equal to 3 times 2 times 60. You need to convert 2 minutes into seconds, and we get 360 coulombs. The mass of a substance deposited during electrolysis depends on the quantity of charge that is passed. Now, according to Faraday law, the mass of a substance produced during electrolysis is directly proportional to the quantity of electricity passed. Now, remember that it is the electrons that carry the charge. Now, conventionally, one electron carries a charge equal to 96,487 coulombs. Now, this value is called a Faraday. And thus, when 1 mole of silver is deposited according to this equation, we require 96,487 coulombs, or 1 Faraday. For copper to be reduced, we need 2 electrons, and therefore we need 2 Faradays. So we have 2 times 96,487. For aluminium, 3 ions are gained, and therefore we need 3 Faradays. So 3 times 96,487 coulombs. So for copper with a relative atomic mass of 63.5 grams per mole, when 2 Faradays, or 2 times 96,487 coulombs, are passed, 63.5 grams of copper metal are deposited. That is 1 mole of copper. For example, calculate the mass of copper deposited when a steady current of 1.5 amperes is passed for 1 hour over a solution of copper 2 sulfate. Now, we want to calculate the amount of copper that will be deposited. The first thing we need to find out is how much charge has been passed. So Q is equal to IT, which is equal to 1.5 amperes times 1 hour times 3,600. 1 hour is equivalent to 3,600 seconds. So that gives us 5,400 coulombs. Now, to deposit 1 mole of copper, we need to lose 2 electrons. So we have 2 times 96,487 coulombs. So 1 mole of copper, which is equivalent to 63.4 grams, will be deposited by a charge equal to 2 times 96,487. So how about if we pass a charge of 5,400? That will give us 63.4 times 5,400 over 2 times 96,487, and that gives us 1.77 grams. 1.77 grams of copper metal will be deposited when a steady current of 1.5 amperes is passed for 1 hour over a solution of copper 2 sulfate. Next, let us find the volume of oxygen gas produced at STP when 2 amperes of current is passed over dilute sulfuric acid for 2 hours during electrolysis. And we are told to take 1 Faraday to be equal to 96,500, and we are also told that 1 mole of a gas occupies 22.4 liters at STP. So let us find the quantity of charge that is passed. Q is IT, which is equal to 2 times 3,600. Convert the hours into seconds, and that gives us 14,400 coulombs. Now, the equation for the liberation of oxygen is indicated here. 4 hydroxyl ions will give us 2 water molecules plus 1 oxygen molecule, and that will require 4 electrons to be transferred. Now, 1 mole, which is equivalent to 22.4 liters of oxygen, require 4 times 96,500 coulombs to generate. From that equation, you can see to generate 1 mole of oxygen, we need to transfer 4 electrons. And therefore, we need 4 times 96,500, which is a Faraday we've been given. So if we passed 14,400 coulombs, how much oxygen will we liberate? So we'll have 22.4, that is 1 mole of a gas, times 14,400 coulombs divided by 4 times 96,500. And that will give me 0.13 liters. 0.13 liters of a gas will be liberated when 2 amperes of current is passed over dilute sulfuric acid for 2 hours during electrolysis. Now, electrolysis is applied in several areas, namely the extraction of metals and some reactive substances. For example, in the extraction of aluminum, electroplating, cathodic protection, and purification of metals. But I'm going to show you the electroplating process. And electroplating is coating of a metal with another using electric current. For instance, let me say I want to coat this iron rod with copper to prevent rusting. Now, it is important to note that the metal to be electroplated should be the cathode. The electrolyte must contain ions or cations of the metal, which is to form a coat on the other. For instance, in my case, I have copper 2 sulfate because I want to coat copper on the iron rod. Now, when I connect to a battery, we saw that copper will ionize into copper ions and electrons. The electrons will flow through the conductor to the cathode. Meanwhile, the copper ions get into the solution. The copper ions move into the solution. Now, to balance that, another copper ion in the solution will move to the cathode and take up these electrons to form metal. Now, this forms a coat on the iron surface and the process continues.
As Curie worked through more uranium-containing compounds, she made yet another surprising discovery. She found that the mineral pitchblende, a uranium-rich ore, displayed such fierce radioactivity that it could not possibly be explained by the amount of uranium in the compound. She concluded that pitchblende must contain another element that was also radioactive and that had never been seen before. The prospect of isolating a brand new element was so exciting that her husband Pierre Curie dropped his own research to help Marie in her quest. In 1898, the Curies announced that they had discovered not one, but 2 new elements: polonium, named after Marie's beloved Poland, and radium, the Latin word for ray because of its fierce radioactivity. The world hailed radioactivity as an even greater discovery than electricity, but little was understood of its potential dangers. In 1903, Marie and Pierre Curie shared the Nobel Prize for Physics with Henri Becquerel in recognition of the extraordinary services they rendered by their joint researches on the radiation phenomena discovered by Professor Henri Becquerel.